Hi colleagues, good morning. On this bright morning, it would be nice for us to refresh our minds with educational material. This time, we will learn the concept of solenoids. For those of you who don't know what a solenoid is, let's look at the following solenoid in three-dimensional view. Have you got the picture? It's understood, okay. The solenoid is nothing more than a wire wound in a circle. We usually wrap the wire around the tube, then take the tube from there. A solenoid is formed. What are we going to do with this solenoid? We will observe the magnetic field formed inside this solenoid. Let's just say, in the middle of this solenoid there is a mica or wooden coaster. This coaster divides the solenoid equally horizontally. We spread iron sand on the surface of the coaster. One end of the solenoid is connected to the positive pole of the DC voltage source. Meanwhile, the other end is connected to the negative pole of the DC voltage source. Iron sand will be attracted to the magnetic lines of force. The iron sand will be linked to each other, arranging itself exactly on the magnetic field lines. We will see the shape of the magnetic force lines clearly from there. This is similar to Oersted's experiments with needle magnets. Pay attention to this section. In this section, the shape of the magnetic field is a circle. This shape corresponds to the shape of the magnetic field in a straight wire. Because this solenoid is composed of a stack of ring conductor arranged lengthwise, the magnetic field in the center is the resultant of all the magnetic fields of the ring conductor. These visible lines of force are the resultant vectors of the magnetic field. We can draw the magnetic field inside the solenoid something like this. In the center of the solenoid are straight lines that are parallel to each other with a certain density. At the end of the solenoid, the density of these lines begins to decrease, because the line spreads to form a circular arc with a wider range. In an ideal solenoid, the density of force lines at the ends is half the density of force lines in the middle solenoid. This is the shape of the force lines inside the solenoid. Magnetic induction is a vector quantity. Apart from having magnitude, magnetic induction also has direction. How to determine the direction of the magnetic induction on the solenoid? In this case, we can imitate Oersted. We can place magnets in the needles at both ends of this solenoid. When an electric current flows, the needle's magnet will deviate to match the magnetic induction at that point. So, the direction of magnetic induction is from the North Pole to the South Pole. Without a needle magnet, this direction can be determined based on the right-hand grip rule. When we grip a solenoid, if the direction of the four fingers is the direction of the electric current, then the direction of the thumb is the direction of magnetic induction. Yup, hopefully this tutorial can provide an overview of magnetic induction in solenoids. And don't forget to watch the next video.
Is this really happening? I can't believe it's true. I'm just as surprised as you.